So today's session is on an introduction to OSPF. So before I really get jumped into the real nitty-gritty of OSPF, I'm going to compare and contrast a bit of the different forms of routing protocols that there's out there. So OSPF is a link state routing protocol. You might have seen or worked with other routing protocols such as EIGRP or RIP. RIP, for example, is a distance vector routing protocol, and EIGRP is an advanced distance vector routing protocol. On some documentation, you might see, especially in the associate level type of documentation, you might see EIGRP referred to as a hybrid routing protocol, but mostly it's just known as an advanced distance vector. So some of the qualities of link state routing protocols is that OSPF is a link state routing protocol, so I just write down that right now. So it's link state. One of the qualities of link state routing protocol is it views the whole network as a whole as a kind of like map, or a kind of like very large graph in which the OSPF process knows, for lack of better terms, everything that's going on in the topology. So everything, as the name suggests, is link state. So OSPF is really just concerned about the state of a link, and it builds out its topology like a map or graph where there's different points, and calculated using a algorithm known as shortest path first, or Dijkstra, which was developed by Edgar Dijkstra, but it is concerned with getting to the shortest path between 2 points or multiple points on a graph. So that being said, does anyone know what the administrative distance of OSPF is?
Anyone want to take a guess?
Right, I guess no takers. All right, so the administrative distance, or the trustworthiness of OSPF is 110. So I'm kind of following along with the official cert guide. I believe it's volume 1. So kind of going in the same kind of format of which everything is described. So OSPF, unlike other routing protocols, breaks routes and other qualities of information into something called LSAs. So link state advertisements. And what LSAs are, you can think about LSAs as different forms of information that put a piece of a jigsaw puzzle together. So you can imagine the whole network as a puzzle, and the LSAs are just little pieces and parts of a puzzle that help OSPF understand how the network is built. And there are various different types of LSAs. If we have time in this session, I'll get to those various types of LSAs. But just know that they're very similar to puzzle pieces in a large puzzle. And everything is, all of these LSAs come together and are stored. So they are stored in a link state database. And this link state database, as the name suggests, it's a database that holds all of these LSAs together. And once this link state database is fully built, then the shortest path first algorithm can be run, and we can choose our best paths or best ways to reach certain types of networks. So in terms of transport, OSPF rides on the network layer. More specifically, it uses IP protocol number 89. So it doesn't use TCP, UDP, it uses IP protocol number 89. And does anyone know the multicast address for OSPF?
Trick question. There's two of them.
Well, the one that all routers in OSPF participate in.
It's 224.0.0.5 and 906.
Correct. Yes, so for general OSPF operations, Chris, can you please turn down your mic?
Yes, sorry.
I'm hearing some echo. Thank you. So for OSPF, the OSPF multicast address, there's two of them, but the main one that we'll focus on right now is 224.0.0.5, in which all routers join this multicast group that want to participate in OSPF and get information about OSPF, any types of OSPF updates through Lsas or through LSUs, link state updates. But all OSPF routers in a topology would join this multicast address to learn about new neighbors, to listen to hellos, and so forth. So as I mentioned a bit earlier, LSAs are kind of puzzle pieces once again, and they are sent in some packets known as link state updates. So link state updates are really when routers are exchanging LSAs, link state advertisements are contained in link state updates. So I'm kind of describing a bit of the different packet types in OSPF. And actually, it's kind of, before I jump in too deep, I'll kind of describe what happens when you enable OSPF on two different routers. So I'm going to draw out a simple topology here, router 1, and put router 2, and I'm just going to have a simple link. Similar to last session, I'm just going to use 192.168.1.0/24, and router 1 is .1, router 2 is .2. And does anyone know what a router ID is? In the OSPF world?
Yeah, it's kind of like what done one done what done that one, for example.
That's for example what could be one, but what's the purpose of a router ID?
Spanning tree.
No. Router ID is used there to identify a router in like an OSPF world, for example. So it's there to identify which router sent what updates, as an example. And it can be, it's written in a 32-bit format, so it might look like an IP address, but they're two separate things. So as Chris mentioned, it might be, for example, 1.1.1.1. It's just a 32-bit number, and it just basically gives some types of identity to a router. So for example, if router 2 learns a route from router 1, more specifically, it will say, I learned a route from 1111, which would be the identifier or router ID of router 1. And for example, router 2 would be 2.2.2.2. Do you guys see my screen, by the way? I didn't ask before.
See it?
Yeah, I see it.
Yeah, we can see it.
Awesome. Give me one moment right now. Right, so did not see any questions yet in the CCNA chat, so we're doing pretty well. So just erase this right here, just the router IDs. I'll rewrite them on the top. So once again, it's used to identify the router in the OSPF network. So just write here, right? 1.1.1, and does anyone know the process in which a router ID gets selected? No takers for the question?
You said which one gets selected to be the big bad, the boss?
No,
I missed the question.
Yeah, I missed it too. I'm sorry.
no, it's all good. Is my audio coming out good or?
No, I was trying to hide a body in a crate.
Oh. So my question was, does anyone know or understand how a router ID gets selected?
Oh,
Isn't it the highest IP that it's selected from?
Yes,
The highest loopback.
but it's a bit more specific than that.
I believe it picks the loopback address over everything else first.
Address.
Yep, so automatically without manually configuring anything, the first thing that it chooses, OSPF router ID, is first the loopback address,
The lowest one, right?
the highest.
Really? Okay.
Yep. So the highest, oh.
Yeah, I forgot it was a loopback.
Yeah, no, it's all good. It's all good. So highest loopback address, and second, in case there's no loopback address, highest IP address of an active interface. Active meaning that it's in up state. It doesn't have to be participating in OSPF. Address of interface in router. And to override all of this would be just the manual configuration. So highest loopback IP address. And if I wanted to set it manually, well, manually would override. So I would just write .0 right here, manually configured. So if I go into router 2 into the OSPF process and wanted to change the router ID from, in this case, I just have it as 2222, I can manually go and say, I want to force you to use, for example, 3333 as an example. Let me see, what else? So that's the process in which a router ID gets automatically chosen. And now I guess I'll move on to kind of like the whole process of a OSPF router being brought up into a network. Let's move this down here and redraw my topology once again. So router 1, router 2, they are connected using 192.168.1.0/24. The router ID here is 1111 because of the loopback I configured. On router 1 and router 2, it's 2222. So what's the first step that happens when the OSPF process is turned on a router? What state rather does the OSPF router first encounter? Yeah, or first go through? What's the first state?
Exchange?
I'm sorry?
Exchange?
No, that's further down the line when we get into forming an adjacency. Right now, we're just talking about getting the routers up. So when I first turn OSPF on a router.
Doesn't it send like a hello?
It does. You are correct. But what state is the router in with OSPF when it sends that first hello? So you know how there's like different states?
It's a two-way state.
Oh man, I've forgotten this. Isn't it like open sent?
No, that's BGP.
You leave me alone, sir.
Can you please repeat what you said earlier, Chris?
I said a two-way state.
The one right before that.
Uh,
You're very close.
One way.
No.
I really I don't remember. I feel so ashamed.
Initiate, something like that.
Yes, it's the init state. Give me one moment. Someone was texting me. So it's the init state in which, let's say router 1 comes up. It will send a packet to, so I'm just going to use a different color. I'm going to draw a green arrow, to 224, the destination address, 0.5. And it will say, it will be a hello packet. And it will say my router ID is 1.1.1.1. In this case, we just have two different routers connected to each other. So really, it'll just go to router 2 if router 2 is participating in this multicast group of 224.0.0.5. So it will send a hello once again. We are currently still in its state. And router 2 comes up. And router 2 sends its hello to 224.0.0.5, but it has received as well, it has seen the router ID of 1. So it will send a hello, and it will say my router ID, my RID, written shortly, is 2222 from router 2's perspective, and it will say I've seen 1.1.1.1. So it's not only sending a hello, but it's telling router 1, hey, I've seen your hello. So router 1 basically switches over to the two-way state, which means, as the two-way state suggests, write it in blue, we go into two-way, it means that both routers, or however many routers in an OSPF network, have seen each other. It's two-way communication, right? So router 1 says, hey, my router ID is 1111, and it can see, once it sends another hello to router 2, saying, oh, now I've seen your RID. So another hello is sent, and it says my router ID is 1.1.1.1, but we're in two-way state now because router 1, which you could say in this example initiated the connection, or initiated was the first to join OSPF and get it going. It'll say, hello, my router ID is 1111, but I've seen 2.2.2.2. Does that make sense?
Yes, it does.
Awesome. So once again, init is the same thing as initializing, and two-way means that there's two-way communication, just like a two-way radio, like a walkie-talkie. You can communicate both ways and have different forms of communication between each other. All right, so in this type of environment, we've become neighbors with each other. Oops, if I can spell correctly. We become neighbors once we've reached a two-way state. Now, we have still not exchanged any topology information. We have not exchanged any routes, but we just acknowledge as neighbors that we see each other. Now, if we wanted to take things even further and exchange topology information, we would have to become what's known as fully adjacent, which means that we both see the topology the same way between each other, and we have exchanged routes and already run shortest path first algorithm. So if we wanted to become fully adjacent, does anyone know what the next step is for the OSPF state machine if we wanted to form an adjacency? I believe you had said it earlier, Chris.
Exchange? The exchange the LSU?
Right before that, I believe you did say it, if I'm not wrong.
Yeah.
We start off with the Xstart
Yeah.
state. So if we wanted to go into fully adjacent full state and exchange the contents of our link state databases, what would happen is we switch over from two-way and we begin to go into Xstart. So in Xstart mode, I'll just write it right here. Router 1 will send the contents. It will send what's called a database descriptor. Does anyone know what a database descriptor is? Or rather, my question is, does a database descriptor contain the full database when exchanged, or does it just contain a list of LSAs?
Just contains a list of LSAs.
Yep.
What'll happen is there's another process. I forgot all the processes, so you judge me all you want. But when it gets this, it'll be like, I don't have those. It'll look at all the LSAs and compare it to its own database and be like, I don't have these, and then it'll exchange those LSAs, and then the connection goes to full.
Yep. So that's at a high level what our end goal is. But yes, so with Xstart, we send a DBD, a database descriptor, and this contains just a brief summary of what our database has. It's not everything specifically, but it's just more of like a summary that is sent to the other routers running OSPF. And router 2 will receive that, and it will go into the exchange state. So I have a question, or a troubleshooting tip rather, tied into a question. Why might I see, I don't know if it was covered in some of the chapters y'all might have read, but why might I see a router stuck in Xstart state? No takers from it? So if I see a router, for example, stuck in Xstart state, that might indicate that we have some problems with MTU. More specifically, when we have two different types of routers that come up in a OSPF topology, they must have the same MTU. So if, for example, router 1 has an MTU of 1400 and router 2 has an MTU of 1500, the routers will not become fully adjacent. Does anyone know why?
Can you repeat the question?
Yeah, so if I see two routers stuck in, or well, a router stuck in Xstart state when I do a show IP OSPF neighbor, I might see, in this case, well, going a bit further, I've kind of gathered, well, it's an MTU problem, but why is MTU important to be the same in OSPF?
Forgive me for maybe diverging down a rabbit hole, but for all network communication, doesn't the MTU have to be the same?
No.
On both ends? No.
No. We can fragment the packet. But in OSPF, we cannot do that. One of the reasons is because it could be, there can be to a certain point, it's not probably like visible like it is topology when you got 2 routers. But in case we might have been scaled to thousands of routers, well, our databases might be extremely large to the point where maybe even sending a database script or sending different types of link state updates might be larger than 1500 bytes. And OSPF does not fragment. It does not have the ability to fragment a packet or break it down into smaller sizes. Does that make sense?
So if the DBD is larger than 1500 bytes, it can't be exchanged?
Well,
correct.
Wait, no.
Well,
no, it has more to do with if the MTU is too large or too small on the other side, it won't accept it.
Yeah, so, yeah. Meant to say that, so yes, your MTU can be any size between both routers.
Okay.
But if we have a different MTU size, and router 1, let's just say router 1, once again, has an MTU of 1500, and router 2 has an MTU of 1400, if it tries to send, for example, a database descriptor that's 1500 bytes, router 2 will have to drop it. And this will keep on happening because we cannot fragment the packet. So we must have to make sure that if we're running OSPF between 2 different routers, that our MTU is the same.
Okay.
Does that make sense?
Yes, thank you.
Yep, no problem. So you might get a question like this, or might encounter this in a production network or something. But just to know, without going into too much of a rabbit hole on my end, that if a router is stuck in XStart, it probably means that there's something wrong with MTU on either side. So our database descriptor is sent to router 2, and router 2 will now see that and send a database descriptor back. So between XStart and Exchange, it happens very quickly when we switch from XStart to Exchange, because XStart is just really trying to initiate the communication and send a database descriptor. But once both sides have sent database descriptors, so router 2 sending a database descriptor to router 1, we switch over to the exchange state, meaning we have exchanged our database descriptors. Now, router 1 will go ahead and see, it's almost, I could say you can think about it like a receipt. Like, well, your receipt doesn't have like all your physical items, it just gives you like a summary of what you bought, right? So that's kind of what like a database descriptor is. It kind of just gives you a summary. And then we will switch into loading, which is a state where we now go ahead and send each other several different link state advertisements, or LSAs. So we compare both DBDs on both sides, and we say, hey, I need this type of LSA or this type of LSA, for example. So it's more of a bidirectional type of communication that happens between both routers. And we go into loading. That's the state we're in right now. And we are sending LSAs in the form of LSUs, so link state updates. So I'll just write it on the side. LSUs, link state updates, contain LSAs. So LSAs by themselves can't be sent, so they have to be kind of like packaged and sent in link state updates. And they'll be exchanged between both sides. Does that make sense?
Yes, it does.
Okay, there's no questions about like the process so far or anything else before I move on a bit. Well, I guess not. I'll just move on. So once we are done loading, we are in full state. So now both routers are in full state, which means both of them have both received all of the topology information they need to have. They both have this exact same database, and now we can go ahead and run Dijkstra's shortest path first to then calculate what is the best path to reach a given network. What is the shortest path in this case? Does that make sense? I guess I'll take that as a yes.
Yes.
Or did you want to say something, Chris?
No, I just say yeah, it's clear. Thank you.
So just as a summary, so again, top down, just so it makes sense. We start off in an init state. We send each other a hello packet with our router IDs and to 224005. Once both sides have, I'll just kind of highlight, once both sides have seen each other's hello, we will switch over to two-way, which means we now see each other's hello, we understand that we're there. And in case we wanted to become fully adjacent, we would begin the exchange process, which starts with xstart. Xstart sends database descriptors. It's kind of in between xstart and exchange. So exchange is like once we fully receive both database descriptors, then we compare what we need, what we might need, and we'll send link state requests, which say, hey, I want to request this type of LSA because I notice it's in the database descriptor, but I don't have it. And the other router will send that LSA in a link state update, LSU. And in this case, we'll be in the loading state since we are sending LSUs, and I forgot to write it down, Lsars. We are requesting information and we are updating information. And then finally, we go into the full state and we run shortest path first algorithm. OSPF does do some maintenance once we have run SPF, once we have made sure that we have exchanged our topology information, our database information. And I'll just write it down, so maintenance. So another thing we do just to periodically make sure the network is doing well between our neighbors and making sure there might not be any other new routers in the OSPF domain, we send periodic hellos. Does anyone know on a OSPF, on a Ethernet network what the default OSPF hello interval is?
It's 30 minutes, right?
For hello. between different routers. So when routers send hellos to each other, how often are they sent?
Is that 2 seconds?
It is 10 seconds.
Oh, 10 minutes.
So every 10 seconds on an OS or Ethernet network, or rather a broadcast type of network that OSPF understands, it will send a hello every 10 seconds. So hello, 10 seconds. And then does anyone know what our dead interval is, or how long we wait before we declare a neighbor dead?
It's like 4 times the hello message.
Correct. So 10 times 4 is 40.
40. Based on the default, right?
Yep, so that's the default on a broadcast network. And Ethernet is a broadcast type network, so any, for example, gigabit interface or fast Ethernet, any type of Ethernet interface, the default will be 10 and 40. Not only do we send periodic hellos just to make sure our neighbors are still up, we flood any new LSAs. So in case we might have added a new interface to OSPF, or maybe removed an interface with the network, we might have added some new networks, we might have removed some. We make sure to flood those out so every router in our domain or area understands, hey, we added a new network, so let's go ahead and sync up real quick and exchange the topology information. And similar to what you said earlier, Chris, every 30 minutes, any unchanged LSAs are flooded. So every 30 minutes, unchanged LSAs are flooded. Meaning, each LSA, link state advertisement, has a specific timer and sequence number that it has been processed and received by the OSPF database. So that means that every 30 minutes, not all LSAs are going to be immediately flooded out. That might overwhelm a link and contain a lot of excess traffic. It might even crash a router, right? So, for example, there might be an offset of maybe, for example, you have 1 second, one LSA is flooded. After 30 minutes have passed, and the next second, another LSA is flooded. And if the default hello message is changed, does the dead interval stay to 40 seconds? I believe not. I believe if you change the hello interval, the dead interval will be 4 times that. So in fact, we'll try that out in a bit once we get into some bit more of hands-on labs.
No, it isn't. You do have to specify what the dead interval will be. It is recommended that you keep it 4 times.
Oh, okay.
It does not do it automatically.
All right, so thank you for answering that, Spencer. So, yep. And we'll go ahead and see that live in action once again, just to reinforce that. But, yep, you will have to. I believe it's only with EIGRP that does that. That where they have different timers, but EIGRP, if you change the hello, I believe it'll also change the.
It won't.
It won't?
Nope. You can have a 7-second hello and a 15-second dead time.
Well, I guess not. I stand corrected then. Anyway, so that's, thank you for answering that, Spencer. So we do have some, once again, some maintenance that happens even after we've become neighbors. And more specifically, fully adjacent neighbors. So, as I mentioned a bit earlier, the default interface type for any Ethernet interface is broadcast mode. Once again, that means that we have a hello timer of 10 seconds and a dead of 40 seconds. So I'll actually bring a topology up. Does anyone know how to verify what our hello and dead timers are in OSPF on an interface? Does anyone know the command? To verify this type of information right here. All right, I guess there are no takers, so let me go ahead and bring my lab up here. And I kind of replicated the same type of topology we have, and both routers are running OSPF. So if I wanted to see what the hello and dead timers are, hello interval and dead interval, I'll just move this up here. I'm on router 1. I have OSPF running right now. So my command would be show IP OSPF interface. And we could be more specific. We could specify G00, or in this case, that's the only OSPF interface we have. And this is a great output with various different types of information that it tells us. So it tells us what line protocol we are in, tells us our IP address, tells us what area we're in. I'll get to areas in a bit, but we can see that since it's an Ethernet interface, our type is broadcast. And going to what I asked earlier, my hello timer is 10, my dead timer is 40 seconds. Based on this output, I can also see other types of information, which I'll get to in a bit, such as my designated router and backup designated router. So there's a lot of important information on this output. I can also see how many neighbors I'm with and how many neighbors am I fully adjacent with. So neighbor count, meaning how many neighbors I have in a two-way state, meaning I see each other, and how many neighbors do I have fully adjacent, which means we exchanged and peered with them and exchanged our full database with. And we can also see who we are adjacent with. In this case, this is the router ID of router 2. Does that make sense?
Does for me.
Yes.
Awesome. So I'll bring back up my screen right here. And I'm going to introduce a concept called a designated router, a DR. Does anyone know what a designated router is or what it's used for?
Any guesses?
Yep, any guesses?
Somehow manages how like routing updates are made for routers on the same subnet.
You are very close. Did you want to say something, Spencer, or?
No, I mean, I'm not going to answer questions. I was just going
All
to
right.
say he's close. He's like on fire. So close.
Yes, you are extremely close. So to give you a bit of historical context, OSPF was created, I believe, in the late 80s, early 90s, when...
Oh.
Yep, so like the original OSPF protocol is well, older than I am. So when it was created in mind that, yes, we wanted to dynamically exchange routes, but we didn't have a lot of CPU and RAM. And when we exchange databases with a scale of routers in the hundreds or thousands, that the RAM might get eaten up a lot because, well, we got to store a database somewhere. And number two, each time a interface is added or taken away, a network is added or taken away, we have to rerun the shortest path first algorithm. So instead of, for example, does anyone know how to calculate how many peers we would have in a full mesh type of network, just like the small little calculation? Any guesses?
I'll actually guess because I want to see if I remember how to do it. It's n times n minus 1 divided by 2.
You are correct.
Okay. Yay.
So going back a bit earlier, our designated router is supposed to help us scale in the network. We only exchange for the specific network or subnet, we only exchange our full topology with a designated router to cut down on full adjacencies. Because maybe routers nowadays can handle having that type of load, but back then took up a lot of CPU and a lot of RAM. So the reason I bring this calculation up is, let's say we have, I'm just going to draw it out real quick as circles, 10 routers. So we got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And we want it to become fully adjacent with 10 routers. How many, let me see how I would ask this question. To become, how many fully adjacent routers would we have based on this calculation? Just plugging in some simple numbers. If we have 10 different routers, if I counted correctly. Any guesses?
Maybe 10.
Well, we're gonna plug in 10 to the equation. So
it's 45.
Correct. So just on some simple little algebra, we got 10, n meaning the number of nodes or routers in this case. So n times n minus 1, so 10 minus 1 over 2. Based on PEMDAS, we do what's in the parentheses first, of course. Take 10 times 9. 10 times 9 is 90. And then put over 2. 90 divided by 2 is 45. So we would have to maintain on all of these routers, if they were fully adjacent, 45 different adjacencies. That does not scale well in the hundreds of routers.
What did you mean by full mesh? Like each router has a connection to every other router?
Every router would have to exchange a full database with every other router. Does that make sense, or did you need a bit more clarification on that?
I mean, how are these routers connected to each other?
Through an Ethernet segment, let's just say. So we just got a switch right here. Switch.
Hey guys, please, what topic are you guys talking about?
Ospf.
All right. Okay.
Right.
So remember, OSPF sends a multicast hello to form its adjacency.
Mm-hmm.
If all of these are in OSPF, think about how many peerings you're going to form.
So because yeah, go ahead.
It's not clicking for me.
All right. Let me see how I can better explain.
So it's a logical full mesh. We're not meaning we're going to take 9 Ethernet cables from every router and plug them into every other router.
Right.
It's a logical mesh. Does that kind of help make sense?
So an adjacency with we're trying to what we're talking about is avoiding having full adjacency with every other router. So we're not.
Yes. So we're
Correct.
talking about how this worked in the before 4 time, like in the 80s.
And full adjacency is
Yeah. So
is what? Can you remind me?
back the adjacency goes to full. So back in the 80s, every router exchanged its database with every other router. So you would have had this going on like 45 times every 30 minutes.
Okay, now it's clear. Thank you.
Yep. So thank you for clearing that up, Spencer. So yes. So as he said, we have a logical mesh. So it's not like everything's physically connected together, but we're trying to be scalable with OSPF without having to eat up a lot of resources. So hence the reason why we introduce a designated router, which all devices in the OSPF subnet will become fully adjacent with. So instead of having this type of scenario where everyone's trying to become adjacent with everyone, for example, just kind of drawing it out a bit here, we have a designated router where, let's just say we have a lot smaller of a network. We just have 1, 2, 3, 4 routers. We got router 1, actually take this and make it router 1 right here. We got router 2, router 3, and router 4. So instead of these routers logically having to make a full mesh with each other, you can see with each other, the only full adjacency that we would have to make in this case, let's just say router 1 is our designated router, we would only have to exchange a full table with router 1. As our designated router, as we are designating it to only fully exchange our topology with, or our database rather. Does that make sense?
So in practice, what that means is if router 3 is missing stuff from router 2, router 1 will supply it.
Yes, you are correct.
So remember how it was a logical mesh? Now it's a logical star.
I see.
Yeah. So what would happen is if, let's say, going to your example, router 2 was missing something, or let's just say this. Let's just say router 4 adds a new network. We just call it network X. We would use a new multicast address to advertise this to the DR. The address is 224.0.0.6, and network X would be advertised to router 1, and router 1 would get that. So it would send this network X, to 224.0.0.6, which router 1 is a part of. Router 1 would turn around and advertise that network to router 3 and router 2. So instead of router 4 having to go to router 3, router 2, and router 1, it just only goes to router 1 when it wants to advertise a new network. Does that make sense, Andrew?
Yeah, it does. This makes me want to ask a question.
Go ahead.
So there's only one DR per area, per OSPF area?
There is one DR per subnet.
So this is where it gets a little tricky. So
yeah.
So router 2, let's say, is just a druther in this scenario for the link for between these 4. If he had another router, say, poking off of him, so let's say router 5 was off of router 2, router 2 could be the designated router for router 5.
Oh, okay.
So it's per. This is why it's called looked at like a graph. So
Mhm.
these line segments are where you're going to see designated router election happen. I'll let Michael kind of flesh that out a bit more. I'm not going to steal his thunder.
No, it's all good. I appreciate it.
Okay, so sorry, just to be clear, you
Mhm.
said the designated router is per subnet and not per area, correct?
The designated router is what? I'm sorry.
Did you say it's per subnet, it's per area?
Yes. So
Okay.
another thing I forgot to mention. I was going to mention it a bit later, just to not, for some of you that maybe start off with OSPF, maybe not to overwhelm you. But in order to become a neighbor, you have to, between two different routers or between however many routers, you have to be in the same subnet. So hence the reason why a designated router is per subnet. So it's one of those kind of like tricky things, but yes, to answer your question, there is one designated router per subnet.
Okay, it's clear now.
Now, just like without getting into politics, just like in certain governments, we have a president and a vice president, as an example. Well, what would happen if our designated router went down, right? It would be a great idea if we had maybe something like a vice president or a backup designated router right here. So not only in this topology, just to maybe clean things up a bit here. So each time router 4 sends network X, it will not only send it to the DR, it will also send it to the backup designated router. So we have two different points of failure rather than just one point of failure. So if there's at least two different routers in a subnet, we will have a designated router and a backup designated router. Does that make sense?
Not really.
Okay, so a backup designated router exists just in case the designated router goes down. So it's just to add, just in case, just to make it more reliable.
Okay, all right.
So does that make sense a little bit more, or do you want me to explain it a bit differently?
No, it makes sense now.
All right. So it's just for scale, just so in case this DR goes down, we still have the BDR. In case this went down, what would become the next DR would be, let's just say router 1 went down and router 1 was the DR. Router 2 would then become the DR, right? In the subnet or network.
Yes, and another BDR will be elected out of the up routers.
Correct. So, to the process in which a DR or BDR is elected, does anyone know what criteria is involved in that process? Like how we know how a DR gets elected?
So I think there's OSPF priority, the loopback interface, and the IP address on the interface.
You are correct. So when we have our priority, let me bring this back up by default, is 1 on an Ethernet interface. So I just ran show IP OSPF interface, and then my OSPF interface. So right here in this topology. And my default priority is 1. Where was it again?
Like 5 lines from the top.
Yep.
Yeah, it's right.
Yep, there you go. So our default priority is 1. It can go anywhere from, I believe, 0 through 255. 255 being the absolute highest. In case we have a tie in priority, then we would select, let me bring this back up. We would select a router with the highest router ID, which in this case would comprise of highest loopback, or the other way is highest up interface. Make sense?
So with some protocols in networking, I don't know what the right word to use is, the lower priority is preferred. So in this case, the highest one is preferred. Is that correct?
That is correct.
And if I'm not mistaken, 0 takes it out.
Yes. So
I do not participate.
Yep, so if we set the priority, I'll just kind of make an arrow down here. If we set the priority to 0, set priority to 0, that disqualifies that router from becoming a designated router or a backup designated router.
Now, here's a weird scenario. I believe every segment still needs to have a BDR and a DR. So I think if there's only 2, it'll ignore the priority and still make it a BDR. I don't remember exactly because this was just in labs where I've seen it kind of be funky about that.
Well, let's check that out. So
I'm trying to remember. I saw this a while ago, so I might be mistaken.
Yeah, we'll find out. So, does anyone know how to check our neighbor relationships in OSPF?
Like CDP neighbor?
Oh
no, you said OSPF, sorry.
Yeah, OSPF. No, it's all good.
It's a show IP OSPF neighborhood.
Yes, OSPF neighbor. NEIG, I can spell NEIGHBOR. Actually, let me just bring this back over here just so it's easier to read. So on this output, we can see our neighbor ID. Our neighbor ID, I set router 2 to use a router ID of all 2s. It has a priority of 1 on this segment between G00. The physical IP address of router 2 is 192.168.1.2. We can see our dead time, so this counts down from 40. So if I refresh this, it'll go down all the way until 30. It should automatically go down, and then it will refresh to that. So this counts down from 40 all the way to 0 to make sure our neighbor is up. And the state of router 2, or our state in comparison to router 2, is we are fully adjacent, and router 2 is our DR. So when we run this command, we are seeing information about our other neighbors from our perspective. And if we check on router 2, we run, what was the command again?
Show IP OSPF neighbor.
Yep.
Oh, you were just.
Yeah.
Whoops.
So from router 2's perspective, we see a router with the router ID of all 1s. Router 1's priority is 1. We are fully adjacent with router 1, but the state of router 1 is it's a BDR. So even though it's an Ethernet segment and we only have 2 different routers, we still select ADR and BDR. And once again, we see a hello time in relation to this neighbor right here. we see the physical address of the neighbor, and we see what interface we are directly hooked off of. Does that make sense?
Yes, sir.
Awesome. So once again, OSPF with our, let me bring my tablet back up here. With our metric calculation, prefers the lowest metric. Oops. So lowest, I'll just write this in white right here. Prefers lowest metric calculated, it just prefers the lowest metric, and this is calculated using our outgoing interface only with cost. Outgoing interface only with each route. Each route. Does right here, so how the metric is calculated, does it make sense, or do you guys need a visual representation?
What metric are you referring to?
OSPF's metric called cost, which it uses to calculate the best path.
Oh, I see. Outgoing interface only with each route.
So it only measures, when we basically add everything up, we only use our outgoing interfaces, not incoming interface, to reach a network. Does that make sense, or I need to represent it visually, right?
I think I get what you're saying. So like, is it just like a value of 1 is added per outgoing interface?
It depends on what our reference bandwidth is. With OSPF, our reference bandwidth is 100, meaning the reference bandwidth is 100 megabits per second. So you can tell OSPF was designed back when 100 megs per second was super fast. But I'm going to steal this topology from the official Strike guide, or this still diagram, and kind of walk through.
Yeah, I think you should do the visual diagram.
Yep, or in fact, let me see if I can draw it out. I should have enough room. So I'm just going to use like the same types of cost metric. So OSPF once again uses cost to calculate best path. So I'm going to use router 1. So router 1 is right here. And we've got router 2. Got, let me see, router 3 hooked up to, let me redraw this so it's easier to read. So we got router 1. We are connected to router 2. We've connected to router 3. Router 4 is right here. And we've got router 8. And we've got router 5 right here. Router 6 right here. Router 7. And we are connected this way. And we are trying to reach router 8's network, which is network of X. And our cost for that interface is 10. So each interface has a cost. And I believe we can verify that real quick before we get into what I was talking about earlier, how the cost is calculated outbound. We can verify this by show IP OSPF interface. And our cost, for example, is 1, since we are using gigabit interfaces. So our reference bandwidth is 100 megabits per second, so we take that as a reference. But we divide 100 divided by 1,000, and we only use integers, which means we only use whole numbers. So our lowest possible our lowest possible value is 1.
Okay. So
So this part makes
So-
sense. I'm sorry.
So does it mean if it's a fast Ethernet interface, then we would divide the reference bandwidth, which is 100 megabits, with the fast Ethernet speed, which is 100 divided by 100, which gives
Yes.
1.
Yes, sir. So
All right.
let me just look up the. Yep. So our reference bandwidth divided by interface bandwidth. So let me just draw that out. So our reference bandwidth, I'll just type in REF or write it out, is 100, which is the default. And we divide it by the actual interface bandwidth, so int bandwidth. So if it's 100 megabit per second, our cost would still be 1. We can change this. I'll show you how to change that in a bit. But that's just something to keep in mind, that we take 100 megabits per second and we divide it by the interface bandwidth. So from OSPF's perspective, by default, a fast Ethernet interface is the same as a gigabit Ethernet interface. Does that make sense?
Did for me.
All right, how about you, Charles? Does that make sense? I guess so. All right. So now to demonstrate what I was talking about, how we only calculate outgoing interface cost. So we're going to draw out some different values. These are just created values. So between right here, router 1 and router 2, we got 30, we got 60, we got 20 right here, we got 5, we've got 10 to reach right here. So 10 to reach network X, so outgoing. Right here we've got 40, you've got 30, 20 right here, 10 right here, 180. And so basically, when we try to add up our way to get from router 1's perspective all the way to router 10, we calculate costs going this way, because these are our outgoing interfaces. Does that make sense?
Yes.
Yep, so we go from basically top to bottom, and we only go from outgoing. So in this case, 10 right here, 180. So we calculate this way, so only outgoing, since we're going this way. Now, that being said, which one is the best path? Is it the left path, so left? Is it the center path? Or is it the right path? To get to network X. So if we add all these up, which path will router 1 choose to get to network X?
So it will take the center path.
It would. And
Yeah.
you are correct. So for the left path, I'll just kind of go through and walk everyone through it. Left path, we take 10, which is our outgoing cost of router 1's interface, plus 180, which is the outgoing interface cost of router 7, plus 10, which which is the outgoing interface, which is network X, which would be 200 on the left. Correct? Does that make sense?
Yes.
Awesome. I just got a quick message right here.
Yeah, that was me. I'm gonna hop off. I'm not feeling particularly great.
All right. Hope you get to feeling better. Take care.
Bye, guys.
Bye-bye.
All right. Center path, 20 plus 30. I'll just go a bit quicker. So 20 plus 30 plus 40 plus 10 should be 100. That's what you got, right, Charles? For the center path or the middle path?
Yes.
Yep. And for our right path, it's 30, 60 plus 20. So 30, 60, 20 plus 5 plus 10 of the actual subnet X right here. That would give us a cost of 125. So which one of these is lower?
100.
Correct. So the center path will be chosen, and that path will be the path that is going to be added to, or OSPF, the path that OSPF is going to choose as the best path. Does that make sense, Andrew and Chris?
Yes, sir.
Yes, perfect.
Awesome. So let me pull up my notes here once again. So now I'm going to introduce a concept called areas. So do any of you know what an OSPF area, or sorry, why an OSPF area exists? Why do we have different areas?
It defines an area with which other OSPF routers can exchange routing information, I believe.
You are very close. So it basically defines how OSPF, or where OSPF routers will exchange our full LSAs and full database within. So the reason they exist is, once again, going back to a historical perspective, there's a scalability problem, as if we have, let's just draw it out. Let's just say we're in area 0. Does anyone know what area 0 is also called in OSPF as another name?
Backbone area.
Correct. So area 0 is our backbone area. And I'll get to a bit more information about area 0 in a bit. And let's just say we have some routers. So we have router 1, we have router 2, they're just connected here. Let's just say we have router 3 and router 4. And they're all kind of connected together. All of these routers within the same area will have to know everything about each other's databases. So once again, if we were back in a few decades ago, that would become a problem, as well, we have to know information about all of the routers in a specific area. So that does not scale well if we have a weak CPU and not much RAM, because we would have to contain all that information. And once again, each time there's a link state change in the network, we have to rerun SPFs. So either a network is added or removed, we have to rerun the algorithm. So that might consume up a lot of CPU and RAM, right? So, so does it make sense? Like why different areas exist, or just kind of?
Yeah, I think so.
Just limiting the size of the information that's exchanged to
Correct.
accommodate the hardware.
So at a high level, that's why areas exist. You are correct. So we might have different areas connected to each other. And let's just say we have area 1 right here. We have area 1. And we have router 5, router 6, router 7. We're all kind of paired together. We're all kind of connected together. Within area 1's perspective, we are going to know about everything about area 1. Now, between area 0 and area 1, for example, router 6 is only going to know about the routes that exist in area 0. We're not going to know about the specific LSAs or specific pieces of information. So from router 6's perspective, it's only going to know about the routes from area 0, but not know about the very specifics. Does that make sense?
So it has an idea of the subnets that are in area 0.
Yes, but not
Okay.
like all like the nitty gritty, like what interfaces are like in area 0 that are advertised, or interface details. So it does understand that subnets exist in area 0, but it does not understand the very specifics. Does that make sense?
Okay. Yeah.
All right. So that being said, does anyone know I'll just kind of redraw this topology out just a bit. Let's make things a bit simpler to visualize. So you have area 0, let me redraw this. I'll draw each router in blue rather, just to make things simpler to visualize. So our areas are going to be in white. So we got area 0, and we've got router. Just say this is router 2, and then we've got router 1 right here, and we've got area 1 right here, and we've got router 3 connected. What type of router is router 1 based on this type of setup?
Is it not called like a border?
Border.
Yep, it's an area border router. Because, so I'll just write this down right here. So area border router, or ABR, right here. Because it connects to different areas together. Does that make sense? So it has at least one interface in area 0 and at least one interface in another area.
Yeah.
All right. What type of, let me see. What type of router is router 2 right here? So router 2.
It's probably a designated router.
Well, I mean, it could be, but I mean from a perspective of what
I see.
type. Yeah, so what type of area in not area. What type of router in OSPF is it known as? If it's just participating in a single area.
Oh.
I'm sorry?
I said I can't remember.
All right. So it's an internal router because it's only internal.
Yeah.
Yeah. So internal router. But not only is it that, it's also a backbone router. Why is it a backbone router? Router 2?
It's an area 0.
Correct. So it's a router that's also part of area 0. So it's a backbone router. Now, what type of router is router 3 right here?
Still internal router.
It's internal, and that's it, because it's not participating in it's not participating in area 0. So it's just an internal router. And router 1 right here is not only an internal router, not only is an area border router, but what other type of router is router 1?
An external router.
No, but you are. It was one of the terms I mentioned earlier.
It's also a backbone router.
Yes, you are correct. So it is also a backbone router, because it is also part of the backbone, since it's connected to area 0. So I'm just going to type
that's true.
BB router for backbone. Now let's say we have EIGRP right here, right? Let's just say it's some type of network. And we've got, say, router 4 right here. Yep, 4. And it's connected to router 2. What type of router is router 2 now? So now that we added some type of redistribution between EIGRP and OSPF on router 2, what type of router is router 2 classified as?
Is it now a border router?
It's a type of border router, but more specifically, you're very close.
Probably inter-protocol, but I'm not sure.
It is an autonomous system boundary router. So it's an ASBR.
Oh.
Because it's connecting two different, you could think of autonomous system as large networks. You'll get more into that in your BGP type studies. I believe the CCNA does cover a bit of BGP, right? Correct me if I'm wrong.
I don't believe it does in the new CCNA, or at least less so than it did before.
Yeah, I believe you might be right. So an autonomous system you can just think of as just like a whole group of large networks, just for sake of simplicity for right now. So an autonomous system boundary router would connect two different autonomous systems together. So we are connecting EIGRP and OSPF right here. Does that make sense why it's an ASBR, router 2?
Yes.
Yes.
Awesome. So from, let's see. So from router 3's perspective, all types of routes that we learn within area 1 are known as what type of routes? So let's say it's got router 5 right here. So we got router 5, got a connection. So from router 3's perspective, if it learns a route from router 5, what type of route is it in OSPF?
An intra route.
Yep. If I understood correctly, you said intra area?
Yeah, intra.
Yep. So routes learned within an area. So within. This is super easy to get confused with inter area. So if anything is learned within an area, this is an intra area route. Now, if let's say router 3 learns a route from router 3 right here, learns a route from router 2, what type of route is it learning if it comes from a different area?
Well, I think you already said it.
Yep, it was
Inter
so
area.
yep, inter area. So inter area, so different areas. Different areas. It's an inter area route. Make sense?
Mm-hmm.
Yep.
Awesome. So, I guess I'll get into like the high level basics of different types of LSAs. So as mentioned before, LSAs are kind of like a little jigsaw puzzle, like a large set of puzzle. And we have different types of LSAs which describe different information. In this case, does anyone know what LSA type 1 is called, rather?
A router LSA?
Yes, you are correct. So router LSA. This type of LSA contains information. It basically describes a router. It tells us at a high level our router ID, our RID. It tells us what interfaces we have in OSPF. It tells us what IP addresses we have with those attached interfaces. So one's just saying we've got interface as part of it, and another part saying, oh, these are specific IP addresses / masks, and our interface status. So for example, if we have an interface that's in OSPF but it's down, well, it will say, when a router describes that specific LSA, it'll tell us, hey, we have an LSA for this specific interface, but it's down, or maybe it's up. So that's important for us to know. Does that make sense? Go ahead.
If a router is sending an LSA, it includes information about all of its interfaces.
That are enabled in the OSPF process.
I see.
Let me see if I can show that. So does anyone know how to verify our OSPF database? What type of command would we use?
Good question.
It will be show
So
IP
it would be
OSPF database.
Yep. So we can see right here our router link states. Based on this output, this is corresponding to our LSA type 1. Reading this information, we can see we have two different routers in our area 0. Let me put my topology back up so I can make this a bit clearer. Do you guys see my even G screen in the back?
Yes.
Yep.
Awesome. So as mentioned before, router 1 has a router ID of all 1s. Router 2 has a router ID of all 2s. So this information will be the same. So our links, this describes our link state identifier. So it identifies the router that's advertising this information. And in this case, our link state identifier is the same as our advertising router. Now, if I want to be more specific and show our type 1 LSAs, I would do a show IP OSPF database. And we've got different options, but the one I'm concerned about right now is the router LSA. So we can see a bit of different output. So we will see right here that we've got, let me see. Let me try a different, or no, this output's fine. So it tells us about our LSA. So we've got number of links, In this case, I've only got one link advertised or enabled, which is just the G00 link for router 1. So we've got our router ID down, so our RID. We've got also our interfaces. So we've got number of links rather, likes to call it here. And we've also got our information about our interface address. And then our specific interface. And we can also see the same information for router 2. So router 2, once again, its link state ID is all 2s that I've configured. And once again, the advertising router is router 2, and it tells us our different information such as our designated router address and our router interface address. So this is the physical address. And we could see that for both router 2, in this case, router 2 is our designated router, is also the designated router. Make sense?
Yep.
Yes.
All right. And I'll pull up this output again, database, just a general database. And now I will get into type 2 LSAs, which are our network link advertise, or network link states, or network LSAs. So our, like I said, LSA type 2. Type 2 is known as a network LSA. So does anyone know why we use this type of LSA?
To describe the network that have a designated router.
Correct. So as I mentioned before, OSPF sees everything as a series of like dots, different routers. It itself does not have, without an LSA type 2, it does not have a way to visualize the protocol itself. It does not have a way to visualize without type 2 what a broadcast network looks like. So we have a LSA type 2 that describes a network that has a DR, in this case, a multi-access network. Does that make sense?
Mm-hmm.
What do you mean multi-access network?
So multi-access as in, think about like Ethernet. So with Ethernet, can you use a switch and logically connect everything to the same segment?
I forget what you mean by segment.
By segment, I mean, from a logical perspective, can you make an Ethernet network make it look like everything's just connected to one wire? Meaning that you can, for example, think about it like with like a hub. You kind of have like everything kind of like sharing the same type of physical cable, but it has to, yeah.
So the answer is yes.
Mm-hmm.
They all can share the same cable.
Yep. Logically, they all can.
Because
Think
of
about it. Yeah.
CSMA CD or
CSMA CD is a collision avoidance mechanism.
so this isn't related to that at all.
Not exactly. It's just more of an analogy where, let me draw it out real quick. So You might have, well, I have this example right here. If I can. So we have multiple ways to access like the same type of network. So we have a switch, right? But it's multi-access. So the switch just is really there just to do the switching. But for all we're concerned, this just looks like all devices are directly hooked up to each other, right?
Logically.
Logically.
Okay.
Does that make sense?
So I understand now what you mean by multi-access, I think. Well, could you repeat your analogy? Or what you're... I've lost the point now.
Oh, no, it's all good. So in this example, it just it's multi-access because from logically each device's perspective, it's all just directly connected to each other, right? Not physically, but logically, router 3 just thinks router 4 are directly attached to each other, right?
Okay.
And broadcast multi-access, meaning that broadcast can exist in this type of network. So that's something apart from, let's say, let me give a better example. You have, are you familiar with like serial links?
No. I know that they don't use Ethernet, but I've never used them.
All right, so say we got one router right here, router 1. We got router 2. And we use the serial link. In serial, and like with, for example, like this type of connection with like a serial link, we cannot have multiple devices on a serial link. It's only one device talking to another device.
Oh, right, of
It's
course.
only a
Serial.
point-to-point link. Yeah, go ahead. I didn't hear that.
Oh, because it's literally like serial transfer of bits. It's using a baud rate.
Not because of that, but just because the way the medium was created. It's just point to point. So meaning from a logical perspective, all we can see is just, oops. Router 1 and router 2. So all they can do is just see each other. We cannot add like a third device.
There are no
like,
switches in a serial network.
Yes. So, or let me use this example, a bit older. So, older Ethernet, we had one wire, right? And we would attach different computers or hosts. So we would have PC1 directly to this wire. And let's say we have PC2. We would have to hook it up directly to a wire. So logically, we can have multiple devices on a single wire, right?
Mm-hmm.
We connected these devices together using wiretaps, or vampire taps, rather. So even though physically it's just one cable, logically we can access devices, multiple devices at once, right?
Okay.
So that's what a like does it make sense, or?
I get what you're saying now. Contrasted with the serial link, you're not describing a point-to-point connection. You're describing a multi-access network where there's multiple devices.
You are correct about that.
Okay, I feel really stupid now. Thank you for explaining that.
No, it's all good. It's one of those things that when I was learning it, I kind of had trouble understanding why a type 2 LSA existed. Because from OSPF's perspective, it just sees everything as just like point to point from like the computational standpoint.
I see.
But a network LSA allows us to have, it advertises DR information. So DR and BDR information. So we can have a broadcast network, or in this case, Ethernet's a broadcast multi-access, because we can have multiple access, right? And we also have a subnet being advertised, subnet ID, and mask. So let's see this in action. So I'll pull up my topology again, and I will pull up secure CRT. And we can see in our database, we got network link states, which are for our type 2 LSAs, so our network LSAs. If we wanted to go further, we can do show IP, OSPF, database, network. And we can see different information. So our link state ID, in this case, is not the router ID anymore. It's the actual, because you remember how we said we can have one DR per subnet?
Yes.
Yep, so that's why it's the actual physical IP. So router 2 has, they're using 192.168.10/24, and router 2 is our designated router. But to describe this type of LSA, our link state ID, we use the actual physical IP address. Now our advertising router is the actual router ID saying, oh, this came from router 2. And we've got our actual subnet information. So once again, I said we were using a /24, and we can see our router IDs. Let's see, our router IDs right here. Does that make sense?
Sorry, yeah, it does.
All right, no worries. And let's say we have a bigger network. So this type of network instead. We have the same type of addressing. So this is 192.168.10. Then we got 1.3, 1.4, 1.5, and so on. So this is a different topology I set up. And I do a show IP OSPF database. We can see a lot more information. Let me go ahead and make this smaller and move this to the side here. So for our router LSAs, we've got our link state IDs, which correspond to our specific router ID. So it tells us, describes the router, its interfaces, and so on. And we can see here we have our the DR, the physical DR IP address of the interface is 192.168.1.6. So right here. And I will do a show IP OSPF network, or show IP OSPF database network. And we've got similar type of information. The router ID of the advertising router, in this case, the router who will advertise this type of LSA is only the designated router. So hence the reason why we only see one entry right here. This is the physical IP address of the designated router, and this is the router ID of the designated router. Does that make sense?
Yes.
All right. And once again, we've got our subnet information. We're using a /24. We can see our attached routers based on the router IDs. And just to show that we have a backup designated router in this network, so I'll just close out. So from router 3's perspective, I can do a show IP OSPF neighbor. And we can see that we have different neighbors. So you notice how I was talking earlier about how for some neighbors, we are only neighbors not adjacent with. we can see that from router 3's perspective, router 5 is just in a two-way state, meaning we see each other's hellos, but we did not exchange our databases with router 5. Because remember how we have a designated router and backup designated router?
Right.
We can see router 4, we are fully adjacent with, and it is the BDR. So our network LSA only comes from our DR. And if I show again, our DR is router 6. Make sense?
Yes.
All right, and I can show the interface properties, some brief interface properties with show IP OSPF interface brief. And we can see, based on this output, similarly, it's we're seeing interface G00 of router 3. We can see we are all in area 0. I can see the IP address of router 3. The cost of the interface is 1. Our state is DR other, meaning that we are neither a designated router or backup designated router. We are a DR other. Make sense?
Mhm.
And we can see we have two neighbors, or sorry, we have two fully adjacent neighbors. So fully adjacent. So we got one right here, which is our DR, and our BDR. We have two fully adjacent neighbors, and we are connected to 3 of them. So we only have 3 total neighbors, but we are, right, 3 total neighbors, but we are only fully adjacent with 2 of them.
Right.
Make sense, Chris and Charles?
Yes, it does.
It does to me too.
Awesome. Let me just back up. And finally, on chapter, what's this chapter again? Chapter 19. Oh, scroll past here. We've got our LSA type 3. Does anyone know what LSA type 3 is called?
It's the summary?
Correct. So it is our summary LSA. So this information contains our subnet and our mask, the router ID of our ABR, and that's really just it. So our type 3 LSAs are therefore our inter-area routes. So you guys remember in this example right here, where I was asking from router 3's perspective, what type of route is a route that it receives from area 0? Yes, no, maybe?
I'm sorry, can you repeat that?
So, do you guys remember in this part right here, how I was describing what an inter-area route was?
Yes.
I'm talking about. So our summary LSA describes our inter-area routes. It is advertised in this case, by router 1, because router 1 is our area border router. It connects 2 different areas together. So area 0, we got area 1, and it takes all this information from area 0. So let me see what other color I can use. Orange. Yes. So it takes all this information from area 0, and all the LSA information, and it makes kind of summarizes it and just tells anything in area 1. It says, hey, here's just subnet and the mask, and if you want to get to it, just get to me, to router 1. Does that make sense? So it described a subnet in another area. So let me actually show you a more hands-on example.
I get that. I was trying to summarize. I was trying to think of a way to summarize all this, not the summary LSA. So all Druther routers send a router LSA to the DR and the BDR. The network LSA is sent to the Druther routers from the DR.
Yes.
And the summary LSA is sent from the ABR to the DR.
ABR to, it could be a DR or any other, or actually, yep, so that or any other directly attached neighbor that it's boundary of. So let me actually move this down, and I'll add another router to the first example right here. So I'm just going to call this R3. And I already used R3, so I'm just going to call it R8. Oh, sorry, I didn't see that. One node. Can't read. And right here, we're just going to call it R3. So let me draw this out. So both router 1 and router 2 are going to be in area 0.
Yeah.
What was that?
So I'll let's go offline. I really had long days. Now.
I'm having understanding you, Charles. Can you please repeat that?
He said I must go offline.
Do you think you can type it out in the chat? So I'm still having some problems understanding. You sound very distorted. All right, let me see what you sent. Yep. All right, no worries. Charles sounds good. He said he was going to go ahead and leave the call. So I hope you have a good one and take care. No problem. Are you other guys still there?
You bet.
Awesome. So I'm going to. Were you going to say something, Chris?
I will say I'm here.
Okay, good. Make sure I'm not talking to a wall. All right. So I'm going to put. I'm building this up from scratch just to give a better example. Things acting a bit weird. So take this, bring it down here so it's in the middle. So I'm going to configure router 3 in area 1. And what type of router is router 2 again?
It's an area border router.
Correct. Let me remove this router 3. I'm just going to. Because it connects area 0 to area 1. Let me move this up a bit higher just so it's, oops. So I can easily pull up the secure CRT window. No, this will take a few moments, so I'm gonna quickly edit some configurations that I made earlier, just configuring IP addresses. If I can find it. Never mind, I guess I closed the notepad window. So what I'm gonna do here is just initially add an IP address to G00 of router 3. No, I'll go ahead and do that for router 2 as well. So interface G0/1 IP add 192.168.2.2/24. So that's what I'm going to use between this link between router 2 and router 3. No shut, and I'm going to save my configuration. And on router 3, hostname R3, no IP domain lookup, on 0, logging synchronous, interface G00, IP add 192.168.2.3, 55.55.50, no shut. Show IP interface brief. We got 2.2, so can we ping 192.168.2.3? Can we ping 192.168.2.2? Excellent. So, how would I go about configuring OSPF on router 3? What command would I use?
Router OSPF.
So router OSPF, and then my process ID. This can be anything you want it to be. It's not like an autonomous system in EIGRP. It's just to give it a process number. So it's not like you have to match these up between routers. You can use anything. You could use 10 on one router and 1 on the other. It's completely fine. In this case, I'm just going to use 1. And how do I advertise and enable a network in OSPF? What command would I use?
Mark?
Yep, sure.
So the command is network.
All right. So network. And
Can you do another question mark?
sure.
Okay, so we're just gonna give the whole network address, so it's gonna be 192.168.2.0.
All right.
And then it probably wants it wants the wildcard.
Mhm.
So it'd be 0.0.0.255.
Correct. Do you understand what we're doing so far, Chris?
Yeah. Yes.
All right. And then I type the area command. What type of area do I want?
1.
Go ahead. Yep. 1. And I need to configure the same thing on router 2 because I have not advertised this network. So using interface configuration mode. So I'll do this. How would I enable OSPF on the interface directly?
With the command
Is it
IP OSPF 1, I believe.
All right. IP OSPF. Our process ID. Right? 1. And then area. And then what area are we using right here between G00 and here?
1.
Yep. So it came up pretty quickly. And on router 2, let's say we want to do the same thing but with the loopback. So if I do a do show IP interface brief, once again, I would go into interface loopback 0, and I want to advertise this network into area 0. How would I do that?
Wait, why do you do this on the loopback?
The loopback just so we can add like an additional network. So like a logical additional network, just so we can have something else assigned to area 0, for example. It's not required to advertise your loopbacks, but it's just something so I can have an additional network to play with logically.
Oh,
Does that make sense?
yeah.
All right, so what would be the command? It's very similar to the other one. I want to put it in area 0.
So it's IP OSPF 1 area 0.
So 1 area 0. So now we can see that router 2 is an ABR, area border router. And let's check the database now. Show IP OSPF database. What do we see here now? So we not only see information for area 0, but we see information for
Area 1.
Yep.
I have a question.
So because, go ahead.
Why did you put the loopback in the area 0?
Just so, as I mentioned to Andrew, just so it's an additional network that we put in area 0. So it's not like an actual like physical interface, but it's a logical interface.
Okay, gotcha.
So once again, so router 2, we see information from area 0, and area 1, because if you are in an area, you have to know all the information that happens within your area. So for example, if I do a show IP OSPF database on router 3 is only internal to area 1. Now if we ignore this output right now, this output at the bottom, we ignore this, we only see area 1 information, right?
Yeah.
We do not see area 0 information as well, like router 2.
Right.
But what do we notice here? What number LSA is this?
3.
Correct. So our summary LSA is there to give us a summary of what networks are in other areas.
Oh.
So you remember how I advertised my loopback into area 0 logically?
I see.
And what about this link right here, 192.168.10?
Oh yeah.
And we can see that the advertising router, our area border router, like I mentioned before, the router ID of the advertising router for both of these is is 2222, which is the router ID of router 2. So show IP OSPF database. And what do you think the next command is to view type 3 LSAs?
Summary.
Correct. So we see summary information about area. Let me see. Yep, so from router 3's perspective, which is in area 1, we see summary information. So we see information about our loopback that we advertised, and then we also see information about the link between router 2 and router 1. So we can see our link state ID, our summary network number, which is our actual subnet, and we can see that our advertising router is the router ID of router 2. So once again, our summary LSA gives us a summary. It cuts everything down for us and tells us, hey, there are some networks that advertise over here, but since you are not in area, since router 3 is not in area 0, you don't have to worry about all the little specific router LSAs for area 0. You just get a summary.
So you have the same information on Air 1, right? For the summary.
Yep, so if you go on router 2, or sorry, router 1 rather, show IP OSPF database. Router 1 is an internal router, right? Because it's only internal to area 0. It's not connected to any other router. So for summary network link states, we see this link right here
Gotcha.
between router 2 and router 3. So if I show IP OSPF database, and what was the specific command to see summary LSAs again?
Summary.
Yeah. We can see our advertising router, our router ID is router 2 because router 2 is the area border router. And we can see our specific subnet that we're concerned about is 192.168.20.
That's really cool. I'm gonna lap this up later and look at make a big complicated multi-area thing and look at all the LSAs. That's cool.
Yeah, so let me see if I can direct you to this resource. It's on Cisco. Let me see. I'm trying to think of what it's called. Understanding OSPF database. It's this amazing guide by Mr. Peter Lumbus. I believe that's how you pronounce his last name. I'll put it in the chat. But he walks through everything.
Awesome.
Not just type 3, but he goes further, maybe further than what the CCNA now covers, but type 4.
Oh, I didn't know there was.
Type 5. Yep, and type 7.
Why is there no type 6?
Type 6 was used for multicast OSPF, if I'm not wrong. It was like some implementation of OSPF for multicast networks. So not for like specific like multicast networks. But it was dropped. Like, no one used it. So
I see.
Let me paste it in the CCNA chat.
All right.
Damn, dude, do you just spend all day reading Cisco stuff?
No, I typically like to do other stuff. Like, I don't know, like sometimes fun things I do, just like simple stuff, like just doing nothing, like listening to music or not much right now, but usually I would hang out with my friends at the park or go eat lunch with them or something, but I don't really game much. So I don't know, for me, most games, like I get bored with them, but learning for me is just something that, I don't know, keeps me going, you know?
I get you.
Some people prefer the game. I guess I prefer to read up and learn about stuff. So hope that answers your question.
Yeah, no, that makes sense.
Yep. So you can go ahead and check that out as well, Chris, if you wanted a bit more of a drill down. Kind of highlights with different colors and explains everything.
Yeah, we'll check this out. Thank you.
Mm-hmm. So besides like the type 3 stuff, I'll go into a brief of type 4 LSAs. Type 4 LSAs. So if I bring this back up, my iPad.
Yeah, I don't want to interrupt you, but I'm gonna die of starvation here. I gotta get up for a few minutes.
Yeah, no worries. So, you know, Chris, how I mentioned that that router 2 right here. Do you see my iPad?
Yes, I see it.
So you know how I said that how router 2 right here, kind of highlighting a bit more, was an autonomous system boundary router?
Yes.
Because it connects. Yeah, go ahead. Were you going to say something?
No, I just wanted to say yes.
Yep, because it connects two different types of routing protocols together. For example, EIGRP and OSPF. It redistributes between them. But it's an autonomous system boundary router. So what a type 4 LSA is it describes how to reach the ASBR. So let me see. So at a high level, a type 4 LSA, so just at a high level for the other LSAs in case you were interested, type 4 describes how to reach ASBR. It's like information about like the actual router ID, and like the actual physical IP address, but it tells us how do we reach in OSPF, how do we reach router 2 so we can get access to EIGRP routes, for example, right?
Mm-hmm.
Does that make sense?
Yes, it does. Thanks.
And type 5, so type 4 was known as, let me bring it up again just so I have the proper terminology. Type 4 was known as an ASBR summary. So this is ASBR summary. And type 5 gives us information about the specific type of route. So it tells us, okay, if you want to reach 172.16.10, what tells us here is a specific external route. So it describes external OSPF routes. So this, once again, type 4 just tells us how to reach ASBR, and type 5 tells us how it actually tells us, hey, if you want to reach 192.168.10, here's a type of route. Make sense?
Yes.
And type 7 is with, I believe this is more CCNP level, but still not bad to go over, is for external routes for NSSA, so not so stubby area. So this is a specific area type. But that being said, I wanted to bring something back up earlier that I said I wanted to bring up, was what parameters, this is kind of circling back to the basics, but once you understand all this, what parameters do we have to match in order to form a neighbor with OSPF? So this is going back to the very basic, but I didn't cover this as there was some other information we had to cover. So basic parameters to establish neighbor relationship. What do you think some of them are that I mentioned before?
The AR ID for sure.
Yep, so we must be in the same area ID. Area ID. So for example, I mean, this is kind of obvious, but just to demonstrate it, let's go in router 3, right?
Mm-hmm.
And let's go into, let's change what area it's part of. So let's just say instead of area 1, we're going to dump it in area 3. OSPF 1, area 3. Do show IP OSPF neighbors. We don't have any neighbors. Why?
Because you don't have any area 3.
Yep, because between this link, between these two routers, router 2 is in area 1 and router 3 is in area 3. So of course they have to match.
Yeah.
So I'm going to put it back in area 1 and it should magically come back up. See? So do show IP OSPF neighbor. Make sense?
Yes.
All right. they must be in the same subnet. So that's obvious. So it must be in 192.168.2.0. But let's say I misconfigured the mask of the actual interface. So we can see right now if I do show IP or do show, I don't know if you've seen this command, do show protocols.
Yeah, I see it.
Yep, so it's for IPv4 information, it's a lot better than show IP interface brief because you get to see your mask. So let's just say this is I'm configuring very quickly, right? Just say at work or something, and I do 255, 255, 255, 128. That's a /25, right?
Yeah, yes.
This type of
Yep.
So see that the neighborship went down to show IP OSPF neighbors.
Yeah, that thing.
It went down because we are in different we configure two different types of subnet masks.
So each area is based on one subnet, basically.
An area can be comprised of multiple subnets. So, for example, let's just say we added another. Well, for example, you remember how we added area loopback or loopback to area 0 earlier?
Yes.
In router 2?
Yeah.
So that one is not in the same subnet. An area can be comprised of multiple different types of subnets. So show IP OSPF interface brief. We have these two interfaces in the same area, but they're different subnets, right?
Oh, yeah. Yeah, you're right.
So we can add another interface and also put in area 0. So let's go back here and let's fix that. So if I put 0, do show IP OSPF neighbor, you can see our neighbor came back up.
Oh, yeah.
We fixed the subnet mask. So this is stuff you might want to go ahead and try out on your own as well and just kind of break stuff and see what happens. Right?
Yeah, I'm gonna lab it for sure. I'm gonna try that.
Yep. And another one, we have to have same timers. So let's say I'm going to change my hello timer. So IP OSPF hello interval on G00 on router 3. I'm going to change my hello interval to 1 second. You remember what the default hello interval was?
10.
Yeah, 10.
Correct. So I'm going to type that in. Let's just say I'm going really quick and mess something up. Let's give it some time to show IP OSPF neighbors. You can see that, you remember how I said earlier this was supposed to reset to 30 seconds?
Yeah.
See, now it's 14 seconds. So it's going to count down to 0 and it's going to drop the neighbor. See? So our hello and dead timers must match. How do we check what we have configured as the hello timer? You remember what command I ran about an hour ago or so?
It was show IP USPF interface, I believe.
Yep. So, actually,
They were wrong.
yep, Spencer was wrong. I'll send it to him. I'll take a screenshot later. No, but it's all good. But as Carl said in the chat earlier, it was good to go ahead and lab it up.
Mhm.
So I guess I was right, but
Oh well.
oh well. Just in case anyone's watching the recording of this, well. Anyway, so we labbed it out and we found out that the dead timer is automatically adjusted to ×4. And let's say we do want to match this. Let's go on router 2's G0/1, and let's do the exact same thing. IP OSPF hello interval 1. Go to router 3. Oops. Show IP OSPF neighbor. Show IP OSPF neighbor. This demonstrates that we can use different timers, but they must match on the link.
Yeah.
So before, you remember how I showed you that our neighbor died? Here we configure the exact same timers. So show IP OSPF interface G0/1. We configure the same timers, and our neighbor got brought up. Make sense?
Mm-hmm.
Yeah. What is the retransmit? That's the LSA timer?
I believe that is the retransmit timer. So, like, let's say,
But for LSAs, right?
yeah. So let's say an interface goes down. If I'm recalling correctly, an interface goes down and it keeps switching back and forth. So up, down, up, down, up, down. At a certain point, it will wait, so it retransmits this LSA every 5 seconds because the link is flapping, right? So it's in that scenario, so we don't have to keep advertising a new LSA every, I don't know, 10th of a second.
Is 5 the default there?
Let's check. So let's check on G00 because I did not modify that interface.
Yeah.
Make sense?
Yeah, it does. What is the wait timer then?
Good question. The wait timer is there in case. So let's say you have this type of topology right here at the bottom. So if you can see like the one where everything's connected to a switch, right?
Yep.
Let's say the switch is down. So everything's connected to the switch, but our switch is down, let's just say.
Mhm.
And router 3 starts the OSPF process. It will notice that there is no DR or BDR on the segment. And it's the only one basically on the link. So in order to avoid like any weird problems, it will wait 40 seconds before it declares itself a DR.
I see.
So it's there to prevent the scenario where maybe there's something wrong with the link. Maybe there's like high packet drops.
So it's based on the def interval, right?
Yes, sir. It's exactly the same. So dead and wait interval are the same. If we went up,
Mhm.
so it kind of waits there and finds out, hey, maybe there's something wrong with my link. Maybe I should wait and see, is there any other DR or BDR before I go ahead and elect myself one.
I see.
In case we have authentication going between OSPF neighbors, let's just do some basic authentication.
Oh,
Plain text.
there's authentication.
Mm-hmm.
I guess that makes sense so that someone can't just plug in a router and add it to Your
Yes.
OSPF config.
Yeah, so in case maybe, well, let's say you've got like a hacker or something with like Kali Linux or something, and they use some type of program that makes their laptop look like a router. We can act like an OSPF router, and all of a sudden we've got the full IP routing table downloaded to our laptop,
I see.
which we can use for nefarious purposes, right?
Got it.
So where was I? So authentication. So I'm just going to do some basic authentication. I'm not sure if it's in the scope of the CCNA, but it doesn't hurt. So I'm going to configure authentication between G00 on router 2 and G00 plain text authentication. There's different modes. So I will start with router 2, IP OSPF authentication. So I'm just going to do plain text, which plain text, well, if you did a packet capture, it sends the password in plain text. So
Very secure.
yeah, very secure. I mean, like I said before, this was created way back then. When,
Right.
Yeah. So authentication, I will, let me see. Authentication key, sorry. Authentication key, and I will type in a password. Let me call this password CCNA, right?
Mm-hmm.
But in order to enable OSPF authentication, I need IP OSPF authentication. So here's just our key, but we still got to tell it we want to use authentication.
Right.
And what do you know? G01, the neighbor of G01 went down because we are not matching authentication settings. So let's go to router 3, and I will go to my gig interface, and I will type in IP OSPF authentication -key, and it was CCNA, right?
Mm-hmm.
And then what's the other command we need to enable?
Chris, do you know?
IP OSPF authentication.
You are correct. And boom, comes up. Now, what are some debug commands that we can use? Maybe they might ask you on the exam or even in real life without having to bounce back and forth between different routers with show configurations. What's one debug command we can use to see what problems we have? So, okay, so let's just say I have no IP OSPF authentication. Show IP OSPF neighbor. Yep, see. So what debug command can we use?
I haven't really used debug commands.
So debug commands you've got to be careful with as, have you ever heard of, this is getting a bit sidetracked, but still really important information. Have you heard of like process switching, fast switching, and Ceph?
Yep.
So, excuse me, at a high level, with Ceph, with certain implementations, forwarding is done using hardware, ASICs, right?
Yep.
If I run the command debug IP packet, I will be debugging. I will be debugging. Me, the router, will be debugging all IP traffic, meaning I will all of a sudden use my CPU to inspect every single little packet that comes in and out of the router.
So your hardware takes a big overhead hit.
Yep, more specifically your CPU. So don't, just one thing with debugs, never run this command. As you will switch from going from Ceph to process switching. which means your CPU will now be involved in every single little packet, which will crash the router.
Oh, really?
Yep.
I guess you could do it in a lab if it's not handling a lot of traffic.
You can. With like the viral images, maybe like on a physical router, it would run better because it has like a physical CPU.
Mhm.
But like here, it would just crash the router.
I see.
This is what's known as a resume generating event.
What does that mean?
It means you're probably going to get fired
Oh,
because you brought a router down, which could have been a backbone router.
gotcha.
So it's resume generating, meaning you gotta
Yeah,
don't ever run this command in production.
noted. Thank you.
Now, certain commands you can run, you just got to be very wary of how much of an impact it will have on your CPU. Now, for the CCNA level and for even some places running debug IP OSPF, hello, debugs are hellos. So we will give it a few moments and we'll see that we sent hellos. It'll give us some output on the console. We can see some various different type of information. It might not show up here, but we're just debugging our hellos. We can see on G00 on router 3, we are sending a hello to this multicast address. Remember this multicast address? The 224.0.0.5?
So SPF.
Yep. So it's sending it to the OSPF. The OSPF multicast address, and we are using area 1 from our physical IP address of 192.168.2.3.
So everything in Area 1 receives this multicast.
Yep, everything that's supposed to be in area 1 will receive this. Now, that's one way to check different information. This would be extremely useful in area mismatch. I'll show it in a few. Now, to turn off a debug, you would just type in undebug all, or undebug your specific debug, but we're just going to turn off all debugs. Now, to debug problems with authentication, we would run debug IP OSPF packet. Now we could just go ahead and enter our process ID and just hit enter and it'll run everything.
Oh.
But we only want to see certain output, right?
But this doesn't change us to process switching.
Not for, if I'm not wrong, not for, well, actually, you use process switching with OSPF because you involve your CPU. So this is control plane traffic. Control plane traffic does go to your CPU. So this won't bother it. Now, data plane traffic, your actual data traffic, if you run debug IP packet, yeah, that will use your CPU. Now, based on this output that we're seeing here, we can see some checksum problems. Let me see if I can go to the top. It's kind of run undebug all, undebug, or you could just type in u all. And let me see if I saw it at the top. Maybe I saw some different output. Maybe I was just seeing things. No, it's the same. So we can see if we see some type of checksum problem, that indicates authentication problems. So we run kind of like a hash. We try to run like a checksum when we configure authentication to make sure the OSPF packet we are receiving has the correct authentication information. So if you see something using this debug and you see some checksum information right here, that indicates a problem with authentication. Make sense?
Mhm.
Make sense, Chris?
Yes, it does. Thank you.
So some useful, or go ahead.
Isn't there an authentication issue because we didn't turn off authentication on both routers, on both interfaces?
There's two ways to look at it. There's an authentication issue because both routers aren't authenticated, or because both routers are not authenticated. You get me? So it could be an authentication issue because we accidentally turned on authentication on one router and we weren't supposed to, or we were supposed to turn it on, but the other router doesn't have it configured correctly.
For sure. What I mean is, isn't that the case though? That we turned it off on one and it's still on the other.
Yeah.
Okay.
Oh, okay. Yeah, I thought you were like asking it more of like a question, as in, yeah. So this would be good to bring up our interface config. So show run interface G0/0, and we can see our OSPF configuration for our interface, and do show run interface G0/1. So one difference here, or what was the wait?
Go back to R3. Yeah, there's no authentication
Yep.
enabled.
You are correct. So I would have to go. So this is stuff they might test you on for the CCNA, Chris. Some of the debugs, so debug IP OSPF hello and debug IP OSPF packet. Because I don't know if they have labs anymore in the new exams, but in the old ones, they might have said, hey, there's something wrong with OSPF, but you can't use show run. How would you fix that? So they wouldn't give you access to show run, because if you did show run, well, you can easily compare, right?
Yeah, for sure.
They want you, like in some cases, to think outside of the box. Think, let me use some different command to make sure, instead of poking around in show run. So make sense?
Yep.
So how does our debug output differ now if we run the same debug as before?
So I take that back. Hold on 1 second. So it was on between router 2 and router 3, right?
Correct.
So debug IP OSPF hello and debug IP OSPF. Well, no, let me. No, you are right. So let me undo this and let me turn off authentication. That's what you wanted to see, right?
I assumed that what you're trying to show is debugging issues with authentication, right? I think that's what you said. So I didn't see where, because the checksum. Oh, I see. Yeah, it was different. It was 6337 and then something else. They didn't match.
Mm-hmm.
And one of them said auth 1 and the other one said auth 0. So I assume auth 0 is saying authorization is off.
All right. So
or authentication.
Yep. So you bring this up. So there are 3 different types of authentication modes in OSPF by default. Authentication. I might pull up a packet capture. Authentication 0 means no authentication. 1 means plain text. And 2 means MD5. Make sense?
Mm-hmm.
So it's telling us 1 has no authentication and 1 has plain text.
Gotcha.
And let me see if I can run a packet capture. Capture G00. Connect. It'll pull up a Wireshark window. So you can see it's plain text because,
Mhm.
and we are using authentication type 1. So authentication type, it's not WebEx. So we loaded up my WebEx. 0 means no authentication, 1 means plain text. And we could see plain text, meaning, well, it's sent. I mean, I guess it's better than nothing, right?
Maybe.
Well, yeah. Nowadays, no. I mean, running a packet capture on a serial link is much harder because it's a different framing format.
Right.
And old routers, when type 1 was created, it's kind of hard to get a packet capture if we're all using serial links. But now, well, we're using Ethernet, so it's just,
Common.
Mhm.
So serial links don't really exist between routers anymore.
They do in rural areas, developing countries, or some areas where they don't have good internet, like a T1 link. Or have you ever heard of a T1?
I do remember a bit of the WAN information from, but I don't recall exactly what that means. I've heard of it.
Yeah, so T1 uses basically like 23, 24 different like copper links kind of all bundled up.
Okay.
And the speed is 1.544 megabits per second.
Gotcha.
So back then that was all right. Nowadays it's terrible. Does the packet capture make sense, Chris?
Yes, man, it does.
So, and also in this packet capture, we're able to see other OSPF information. So, running OSPF version 2. This is a hello packet. And it tells us information about our subnet. And we saw some other information. So we have our active neighbor, our BDR, backup designated router IP address, and our designated router IP address. So this is some of the information carried in a hello packet. So show IP OSPF neighbor. And yep, we're doing good. So show IP OSPF neighbor. So in this case, the dead time's like at 3 because, well, we set the hello time to 1 second and the dead time to 4. So every 1 second, this shouldn't go anything below 2 seconds. Remember, between this link right here,
Yes.
and yeah, we see some good, besides this output, we can see, let's say we wanted to restart the OSPF process on, or before that. Let me see if maybe you guys were paying attention earlier. And if not, it's all good.
You're not going to hit us.
No, not anything. It was something that I kind of like mentioned in the very beginning, so maybe, I don't know, I kind of overwhelmed in the beginning a bit, trying to explain some concepts, but it's all good if y'all don't remember what I was talking about. I'll explain it anyway. Give me 1 second. So what happens if I run show IP OSPF neighbor and I see a neighbor in xstart state? What might this problem indicate?
I remember. Chris, do you remember?
No, I don't think so.
I think you're talking about the MTUs not matching.
Correct. So if I pull this up all the way, so I kind of emphasized it. So
Oh yeah.
if you can read my terrible handwriting, right here where it says xstart.
Yeah, I remember now.
Yep. So if I'm stuck in xstart on any router, there can be multiple things, but the one they're probably going to hit you the most with, and in most environments might be true, is there's an MTU mismatch. So if I show run interface G00 and go on router 2 real quick, show run interface G0/1, and compare these two outputs, what's something that I notice here up at the top on router 3?
Yeah, you changed the MTU.
Yep. So if I change it, what's the default MTU on Ethernet interface?
1500.
All right. It's the default. So if something's the default, in some cases it won't show up. So I might have to clear the process. It's kind of still thinking about it here. So if I run this command, clear IP OSPF process, sometimes you might have to do this if OSPF is acting up a bit. This will restart the state machine for OSPF, so it will go through init, two-way, xstart, exchange, loading, full. Oh, well, never mind. I didn't have to do that. So what do you see now? It's fully adjacent. So before was here xstart.
Start, yeah.
And if we wanted to see the packet capture of OSPF starting up, so seeing some of the different packets, you might have seen them earlier while I was working through this. To restart the whole OSPF process, you would type in clear IP OSPF. We want to restart the process. Yes. And you remember how I was talking about the different packet types? Oops. So we have a hello packet, we have an LSU, link state update, and it tells us different types of information we might want. Let me see if I can make this bigger. So if you had physical gear, Chris or Andrew, you could run like a switchboard analyzer and capture this type of traffic. So we can see our. Were you going to say something?
What's a switchboard analyzer?
What we're basically doing is, let me draw it out. There's the thing of the side. I believe it's still covered in CCNA or if not CCNP. You have a switch, right? You have a switch right here, and you have a router connected to switch, right? we would have, let's say we wanted to see what's off this interface. So this is interface G00, and we have a PC here, G0/1. And we wanted to see what's going on in this area, or this, not area, well, area, but interface, this type of segment right here. We would configure a Switchboard Analyzer that says, any traffic that's in this interface, I want you to mirror it to this interface. So if we have like Wireshark running on PC1,
I see.
we can copy all this traffic from G00, put it on G01, so the PC right here can receive that and basically look through what we're doing. Or if you have EvenG or GNS3, you can do the same thing with packet capture.
Cool. I didn't know you could do that.
Yeah, it's pretty cool. In this case, we're just directly, like logically just capturing off the actual router.
Right. Because it's a virtual.
Mm-hmm. And in this process, we're seeing different hellos. As I was talking about earlier, database descriptor, we've got an LSR, a link state request. We are requesting information about IP networks, these two IP networks. So you can actually go ahead and run a packet capture and see what's happening on the back end. So right now we've got link state update. It contains one LSA, and it's an LSA type 1. And it tells us this type of information. So we would see these packets when we first bring up a neighbor between a link. And then with each LSA or each link state update, we would use a link state acknowledgement to say, hey, okay, I've got this LSA, so I send you an acknowledgement with a sequence number. So we go through the checksum and it's correct. Actually, this is for the authentication, but for the actual acknowledgement, it basically sends it back saying, this is what we received. So this type of LSA, and it acknowledges it by sending it back to the source router.
Would it be retransmitted if the LS acknowledge was different?
Mm-hmm. It would be retransmitted in the loading state. So it would say, hey, maybe this got corrupt. I need you to resend this. So I'll send a link state request, and the other router will send me that link state advertisement in the form of a link state update.
I see.
Make sense, Chris?
Yes, it does, man. Thanks. That's pretty cool.
Yep. So just as, yeah, it's pretty cool stuff. So just as a quick recap for, I guess, today's session, to form a neighbor, in OSPF, we have to have same area ID. You can spell correctly. Same area ID or number, same area number. Same area type. So just a normal OSPF area, not like a not so stubby area or a stub area. We've got to have the same subnet mask, so same subnet and subnet mask. So subnet mask is extremely important. Same timers. Same authentication. And for a high level, that's about it. Oh yeah, and same MTU. Make sense?
Yep.
It's awesome.
So I guess I basically demonstrated almost all of those different parameters.